For today's video, we are looking at linear relationships and how to use data tables to analyze linear patterns. Our essential question today is, how can data tables help us identify the slope and the y-intercept for linear relationships? Please take a moment, pausing the video if you need to copy down the topic and essential question into your header, along with today's date, set up your question column and your note column, and resume the video when you're ready to begin. So linear relationships, as we've been talking about in this unit, is a pattern between two variables or a relationship between two variables, most often represented by the variables x and y, but those can of course change. And it makes a linear pattern if it changes at a constant rate. That constant rate of change is what we refer to as slope. So what we're learning is how to represent these linear relationships in graphs, equations, and tables. And the most common equation for linear relationships is y equals mx plus b, where m represents the slope, b represents the y-intercept or the starting value, and we use the variables x and y as the two quantities that we're comparing in the pattern. So let's go ahead and take a look at our first example. For our example 1, we are looking at a tile pattern where we're trying to determine the number of tiles for any given figure number. So this is kind of a common way to start looking at linear relationships and patterns. And so what I've done here is we have a pattern. Each square is considered a tile, and the figure number here is just telling us like the starting value. So at figure 0, this pattern starts out with 3 tiles and then moves on to figure 1 where it has 5 tiles altogether. And so I just want you to take a moment examining this pattern and see if you can figure out how many new tiles does it add for each new figure, and what would figure 4 look like. Pause the video to think about that and see if you can draw in this pattern and then make some notes about that as you think through this pattern. If you said that this pattern adds 2 new tiles for each new figure or something along those lines, I would agree with you. And I've gone ahead, this is our starting figure, so figure 0 has 3 tiles. But after that, for each new figure, it adds 2 tiles to the bottom left and top right corners in this diagonal line here. And I've gone ahead and highlighted those. So if we continued the pattern, figure 4 would look like this, and would have 5, 6, 7, 8, 9, 10, 11 tiles. So let's go ahead and make a data table to represent this pattern and see if we can turn it into a equation that in the form of y equals mx plus b. Alright, so I've gone ahead and started a table, which you'll want to definitely copy in as well. And so for this pattern, we're using the variable x to represent the figure number. So we have figure 0 through 4 represented in the x column, and we're using y to represent the number of tiles, because the number of tiles depends on what figure number we're talking about in this linear pattern. And it is a linear pattern because it constantly adds 2 new tiles each time. So that pattern stays the same, and it's the same amount all the way through. So that's why this is an example of a linear relationship. What I'd like you to do is go ahead and see if you can complete the rest of this table. So figure 0 has 3, figure 1 has 5 tiles, figure 2 has 7, and then go ahead and fill in figure 3 and figure 4. Excellent. So we should have that figure 3 has 9 tiles, and we can count those up, and figure 4 has 11 tiles. So the next step is we're trying to represent this pattern, which we've made a data table, but we want to be able to interpret that as a equation that represents this tile pattern so that we could use that equation to figure out how many tiles are in any given number, any given figure number. So the first thing we're going to want to do is figure out the slope, right? So slope is represented by the variable m in the equation, and we again find that by making this comparison between how does y change compared to how does x change. So the change in y over the change in x. So we're just going to make some notes here, and you might already know because we've actually discussed it here, but let's go ahead and see if we can put some numbers to that and fill in our slope. And then we'll fill in our y-intercept to be able to complete our equation. So I've gone ahead and laid out our work here, analyzing how this table is changing as it represents our tile pattern. And so what I noticed is that the figure number is just changing by 1, right? We just went one more figure over. So 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4. And so our figure numbers just increased by 1, so that's our change in x was adding 1 each time. And our number of tiles, our y, our change in y, was that it was adding 2 new tiles each time. So it went from 3 tiles plus 2 more to give us 5, plus 2 more to give us 7, plus 2 more to give us 9, plus 2 more to give us 11. So our change in y would be 2. So we can set up a data table to represent any pattern. Sometimes we're given the data table, sometimes we have to look at something like a pattern, a picture, or a word problem, and we have to create the table. But once we create the table, we just then can look at, once it's organized, how is the y value changing, how much does it change each time, and how much does the x value change each time. And this will be how we calculate our slope from a data table. So let's go ahead and fill that in. So it's changing by 2 tiles for our change in y for every 1 figure. And actually, if we look at that value, 2 over 1, that can be simplified to just be 2. So our slope, in its most simplified form, when we compare the change in y to the change in x, is 2, because 2 tiles for every 1 figure, 2 divided by 1, simplifies to 2. And now we just need to find the y-intercept. You might remember from a graph that our y-intercept is where it crosses the y-axis, or when the value of x is 0. And so in our table we can see that when x is 0, our starting figure, when we first look at it, it has 3 tiles. So this, right here, 0, 3, this would help us give our starting value. This will be our y-intercept. So our b value for this equation is 3. So the last thing to do is take our slope calculation and our y-intercept and plug it into the equation. So if we replace m with 2 and b with 3, we've now taken this linear tile pattern, analyzed how many tiles it changed or added for each new figure number, and created a table to represent that, showed our work of how we calculated the slope by analyzing the change in y, the number of tiles in this case, but to the number of, for every new figure number, our change in x, wrote that into our slope form, found our y-intercept by looking for when x is 0, what is that y value, so we know that it starts out with just 3 tiles, and wrote that into the equation y equals mx plus b, so we could now use this equation to figure out how many tiles are in any figure. If I wanted to know how many tiles were in figure 50, well, x equals 50, so I could say, well, 2 times 50 equals 100, plus 3 equals 103, so, if I wanted to know figure 50, it would have 103 tiles. So that's why it's important to be able to look at any kind of pattern, find a way to organize it, data tables are really nice, and then be able to write an equation. So I'm going to have us leave it at that, our first example. So if you would make sure that you have this all copied in to your notes, make sure that you have that complete, go ahead and fill out the summary, and we will continue to look at how data tables can help us analyze linear relationships so that we can represent them in any of these three forms, depending on which is the most helpful for the given situation.